Hello everyone. This video is for the doubts I had received for my previous video. So there were some commands and some steps on which I had assumed that audience may be aware of that and from the flow of creating a container the explanation got skipped. So I have included all those things in this video. So let's start. So while creating our container, we had one step sorry like while creating our container we had one step at which we had to do mounting, like we have to mount proc, we have to mount sysfs and tmpfs also. So what exactly is happening here? So let's understand. This particular command, mount type proc, is executed when we create our container. So this mount type proc is mounted on /proc and it uses a particular directory for that. So here this particular directory can be anything, and we have mounted this proc type file system to this particular mount. So what exactly is this proc type file system? It is a virtual file system. So a virtual file system is a file system which does not have any files of its own, but basically it acts as an interface between your user space and kernel. So whenever you interact with this proc mount point, kernel will execute some processes, and by those processes it will populate the contents of this proc folder. Like while mounting, you are creating a virtual file system and that expose live kernel data structures and system information. So by virtual file system, live kernel data structures are basically presented to the user space and also the system information. So by that, this /proc or /system acts as an interface to the kernel data that are dynamically generated when you access them. Let's further understand it. Like when you create proc file system, you can have content like this: 1, 2, these are the process IDs, current process symlink, CPU info, memory info, uptime, and whatnot. These are not the real files. Like if you check over here, basically we have not yet mounted. Let's mount type proc, and let's give a gibberish name to it and keep the mount point at proc. See, it will still work. This particular PIDs, if we check list/proc, we can see we have these particular process IDs 1, 13, 7, 8, 9. These process IDs are dynamically created by the kernel by reading all the CPU stats and other things. So continuing here, like, okay, I have said these are not the real files. We can understand it by taking example of ls, like taking example of a proc process called uptime. So let's take its example. If we do cat process uptime, so this particular uptime is dynamically generated by kernel. Like if I execute it again and again, see the values are changing because these are not hard written. And if you do list proc uptime, see, it has size 0. So how can these many contents, let's print the size of all the contents. You can see most of them has 0 size, but I have just shown you the uptime has the values. So how come it has 0 size? Because this proc here is a virtual file system. Now it has become like when we have executed that mount command, this particular mount has become interface point for the kernel, so that kernel can communicate with our process and populate this much information to us. Likewise, if we do mount system file system, write any gibberish here /system, so that's how we are able to get the devices information. And same goes for type temporary file system, where we are creating a file system mount. So by that, our file system will be in the separate mount. So again, going back to our theory part. So whenever I have done list proc, values are generated in real time by the kernel, and it creates directory entries for each process that I have just shown you. Apart from that, similarly, /sys/ temporary mounts are done, and /sys mount watch for devices, and temporary fs mount watch for file system. And apart from that, there was also --fork statement in our unshare command that we have executed to create our container. So why fork statement was executed? Fork statement was executed because if we do unshare process ID without using fork, like here, the cell itself is not in the new process ID namespace. Like the new process ID namespace do get generated, but the cell process will remain in the parent namespace. So for cell process to be available in a separate namespace, we have done --fork after our all unshare commands. So fork is done. Next, now study IPC namespace. So IPC is nothing but inter-process communication. Suppose there were two processes, P1, P2, they are executing. So any communication between these two processes is done by IPC. So IPC has two types: system 5 IPC, which has three ways: shared memory, message queue, and semaphores; and POSIX IPC, shared memory files in dev/shared memory. Like message queue and semaphores are not we are going to discuss today, but like message queue is just like your simple queue in which you can share messages between different processes. Semaphores is a concept by which you can allow different processes to access some data of critical section, and when semaphore value become less than 0, you can prevent those other processes to access that critical section, and when semaphore value get incremented, the other process can also access the critical section. So here we will study the shared memory type IPC. So what we will do, we will create a 64 MB shared memory in our host system, and like here this 64 MB memory is created. P1, P2 process both can use this shared memory, and by using this shared memory they can have a communication between them. So that is IPC. So we will create IPC in our system. Let's go and create. Like here, if we do IPCMK, IPC make -m 64M, shared memory ID is 1, IPC-m that list, the shared memory ID is 1. And because we have started this particular container using -IPC, so here we expect that same shared memory should not be available, and likewise that shared memory is not available here, although in host system that shared memory is available. Like here shared memory id is 1 because it has started with 0 when, like, before recording video I had executed it first. So in your system it will start with 0. So now let's go on and remove this particular shared memory space. So now in our host system also shared memory space is deleted. So by that we were able to understand three concepts. First one was mounts, second was fork, and third was IPC. And if I like elaborate mount again to you, so let's do it again. Whenever when I executed this particular command, let's say mount type proc, then taken some arbitrary directory to a mount point proc. What exactly has happened is this slash proc become a gateway between my user space and kernel space. Whenever I interact with this proc mount point, kernel executes some processes, gets data, and updates that data in the proc folders. So that's how this particular mount point was able to show process ID starting from 1, because in our host system process ID may have started from 2873, but here process ID started from 1 because this slash proc mount point taken into account the namespace of the container, not the host. Okay, so I believe this mounting thing is clear now. So thank you.